This video is a demo of the PathFinder project, which is essentially a platform that allows users to analyze and create visualizations of large-scale networks. On the homepage we have an overview of the project, along with a features list and some motivation behind creating PathFinder. Let's start by clicking Try It Now. This page is where the application parameters and controls are located. Let's start by opening the left and right nav bars. On the right hand side we can see there are two core algorithms behind this program, k-simple shortest paths and shortest paths minimum spanning tree. Upon opening k-simple shortest paths, we can see the basic algorithm parameters. These parameters allow for minimum interaction to get started, while the advanced controls hidden below allow for greater functionality. Let's go ahead and click on some of the advanced controls. The search space reduction 1 and 2 parameters allow us to adjust the program's heuristic to determine how many vertices to include as critical vertices in the search. The more vertices that are selected, the higher the runtime and accuracy of the analysis. The visualization parameters below allow the user to determine the scope of the resulting visualization. This can range from a sparse graph showing only the core path relationships to a full graph with multiple levels of depth. We'll show examples of both sparse and full visualizations in this demo. On the panel to the left, we have some additional network parameters. Starting at the top, we have options to remove vertices and edges from the search query. Below that are multiple visualization color schemes and size options. At the bottom, we have an option to reuse the current graph computations for future analysis. We'll show an example of this feature later in the demo. Let's go back to the right panel and start by selecting Alon Levy as the start vertex and Michael Schmitz as the end vertex. This program is able to process numbers as well as names. However, for this algorithm, we'll focus on names. Let's search for 3 paths and look at a depth of 2. In this example, we'll use the default advanced parameters along with the DPLP co-authorship network with names. Next, we'll click Run and wait for the results. It should be noted that this DBLP dataset using names takes a few more seconds to load into memory due to its large size of 320 megabytes. This is especially so compared to the DBLP dataset using integers, which is rather small at 14 megabytes. Now that the program is done, we'll hit the Visualize button and wait a few moments for the rendering. Okay, now that the visualization is finished, let's start by zooming in a little. In red, we can see the start and end vertices. The orange vertices are part of the shortest paths, and each path has a distinct color in order to identify it. The key neighboring vertices algorithm determines important vertices in relation to these paths, which have been highlighted in purple and blue. Purple vertices are a depth of 1 away, and blue vertices are a depth of 2 away. Now we'll run the same test reusing the current graph results along with different visualization parameters to highlight only the core path connections. This can help when the visualization is overcrowded, a little bit like it is now. This time we can see there are no longer any vertices surrounding the paths. In addition, we can see that this is much faster to compute due to the graph reuse. Next, we'll show the shortest paths minimum spanning tree algorithm. We'll use 3 numbered vertices in this example: 0, 9, 5, 1, 3, and 14, 2, 2, 1. And select the DBLP dataset instead of DBLP with names, since we're using integers instead of strings. In addition, we'll select a smaller vertex size and change the color scheme to 1. We'll also turn off some computation reuse functionality, as it doesn't make sense to use it here. Now I'll click Run and wait for the results. Now the analysis is finished, we'll click Visualize and wait a few moments for rendering. This time the vertices are significantly smaller, however each one can be viewed by zooming in. Let's do that now. We can see the 3 chosen vertices in red, along with the intermediary vertices in orange. The default visualization parameters show the key neighboring vertice in relation to the tree at a depth of 2. Detailed instructions on the advanced parameters and how to set them up can be found on the instructions page. Thank you for taking the time to watch this video.